Okay, so I'm going to recap most of what we had yesterday, just in a more brief manner, because we need to have this fresh in mind when we continue. So I presented the spectral element method for the acoustic wave equation. The acoustic wave equation wrote or used rho, so the density at position x times some kind of displacement at position x and time t minus the spatial derivative of the elasticity parameter mu of x dx t equals some kind of driving force position x time t. So that's where we started. And also to define them, x here is from 0 to L, and time runs from 0, 0 to capital T, some kind of time. Then we used Neumann boundary conditions and initial conditions that everything should stay quiet, meaning that the fields at time 0 is 0. Oops, quiet. So that's the start. Next, I introduced the notion of so-called complex supports, and that's mostly is the detail for the math to work. But what we do, we multiply this function here with some kind of test function, just a test function, and this test function is also going to be part of our basis functions later. So what we had then, and also we integrated over base. So we ended up with this W, my test function now, rho, double dot, x minus, yeah, and we also did some partial integration such that we got away with the boundary condition. Ended up with this W times U dx of U gx on here equals driving omega 9 f dx. Okay. So that was just a mathematical trick we did. Okay, later we placed all of these test functions, which needed to have complex support, with basis functions, which is just a subset of the test functions we can use. What we end up with then are these, I think I called them J, here and J. So this is just a trick we do. Next, we use the so-called Galerkin projection, which is basically splitting this U into an approximate solution. An approximate solution is sum of some kind of temporal coefficients. So I of p times the I of x, and this should be approximately equal to the exact solution. Okay, and next we basically replaced these things, and then we ended up, where are we now? Yeah, we also require that this approximate U solves this equation, or we can actually insert it. That's more like a formal requirement. Okay, inserting this into into the weak formulation, we ended up, see, so we have to sum over all of the basis functions there. I, n, and since u of t is just temporal now, we can move it outside of the integral. Rho j as a test function, and then I as a basis function. Dx plus sum I equals n ui twice time g dx j x I dx should equal this driving force j f dx. And this should then hold for all of these functions. Okay, next we talked about how we wanted to set up this interval, so 0 to L into disjoint elements G1, 2, 3, and G4. Does this feel familiar? Good. No, that's the thing. They don't have to be of equal length. That's the good thing with, well, finite element methods, that the elements doesn't need to look like, well, other ones. Because if you have a lot of variation, for instance, in your last element, you could cut this into tiny, tiny, tiny. But you don't need to have tiny, tiny, tiny elements in your whole interval. So you save some computational time. 4, 5, 6, 7 there, if you want. Okay, and then we focused on just one of these elements. So this is for the full interval from 0 to L. Next, well, cut it into pieces. And we got this, we needed to sum over each of the elements. If I just modify my equation here, it is basically that we replace these where I sum over all of the elements. E okay. Problem we had now is that each of the temporal coefficients are dependent on all of the whole interval. It was difficult to break apart. So that's why we used basis functions that only have support in one of the elements at a time. Or, well, for all time, but yes, they only have support on one of the elements. And the ones then, this one. So we used a lot of, well, we ended up with an E, which is the amount of elements, times n1 basis function. Because we just said that we wanted n plus 1 basis function. So that's this small n here, here. total amount of space. Yeah. And then we said that we don't want to solve this equation for all of the elements. We just want to compare them with a reference element. With some kind of reference element. And in order to do this, I had to also construct function. So if I go from, so this is part of one element, E, where the x's live. This is our reference element. Nice. Live. And then we arbitrarily said that the forward transform should be from the reference element to our real space. So I call it real. That's where we're doing our simulation. So we have a different transform for each element. One transform. Oh, element. I've been using it a lot now, so I thought I didn't explain it. No, it's just shorthand for element, ELT. Okay, and we figured out that this transformation E I A over 2. So this is similar to when we did the Gaussian quadrature plus for each of the elements. So this should work. E. Because AE and BE, they change for the interval. So this first one, that goes from, let's say, 0 to 1. The next one, 1 to 5.5, and then 5.5, 6, maybe. That was just random numbers. Okay, and then we use this transform to actually transform our weak solution of the wave equation. Then we ended up with, please bear with me, 1. Now we say that we have n plus 1 instead of small n. I at element E is a temporal coefficient. Now we're on our reference element, so the integral, instead of going over element G, it goes from -1 plus 1. Rho, we also need to transform E. I at dx. Also, as a side note here, is we're using this transform here, we need to do the integration over xi. Have that x is the same as 1 times dx. Yes? dx dx. Still with me? dx equals dx divided by b. So that's where that part is from. Okay, we also need the next one. First one. Plus 1 transforms or test element okay, and 2 now. We're basically just applying this many times. So you see we're also differentiating with dxc down here. So we're doing the same for these two. Good. X squared dx dt then equal to our driving force. 1 plus 1 c j e d f of e dx d. Oops. Okay, so we're almost there. You see that this is, in essence, similar. Okay, so you see the similarities between this form and this form. Only here, I mean, this looks more complicated because I'm also including all of these transforms inside it. So here you still have J, P, I, you, only that it's in your kind of real domain and not in this reference element domain. That's what these mean, that you are doing, for instance, this mu, you have to transform your real one into this reference element. that just looks more complicated. Okay, and I think we ended as saying that these I, X, V are so Legendre polynomial. So going back to relation. Again, minus 1. Yeah. That's so you can only do, you only need to do stuff at the reference elements. So all of the math later is going to be done on a reference element, and then you can just transform it. So instead of having computing coefficients, so these basis functions for each of the elements, you can just have a set of basis functions on a reference element, and then use your the transformation to get back to your real. So it how to say this? It complicates it apparently complicates the problem, but in the end it makes it easier to solve. It's only that you have to keep more stuff in your head at any time. So we get to this now. It was the same when we did the Gaussian quadrature, where we had this kind of reference element going from -1 to 1, and then we had T space instead of this big lambda space with size. Remember? Okay. So what we used there when we did the quadrature is we had to look up on a table in order to have the appropriate interpolations. Okay. So we had a lot of coefficients, and actually calculating these coefficients, that's also tiresome. It's easier to have these coefficients for some kind of reference element and then look them up, instead of having to calculate, oh, what are the, it's called Gauss-Lobaudo-Legendre points. That's just a name, but it's in order to suppress the Runge's phenomena and also increase the accuracy of your solution. Okay? So I can, so if you want to do an approximation of polynomial degree 4, see, so having this of degree 4, poly-deg 4, then we have the co-location points 0 plus and minus 1/7 square root of 21 plus minus 1. Again, maybe just, let's say these are co-location. Points. Okay. If you want a polynomial of degree 5, then you end up with plus minus. What you're doing here, you're searching for roots of some kind of polynomial. Plus minus 1, 7, 2, and plus and minus 1. Okay, so these are just some very simple examples of them. The difference between these points, so these are called GLL points. The difference between the GLL points and the GL points, so the Gauss-Legendre points we had earlier for the Gaussian quadrature, is that the Gauss-Lobaudo-Legendre points also include the endpoints, plus and minus 1. So you force them to also include the endpoints. And we need to use the endpoints in order to enforce continuity in our solution. This basically means when you've done the transformation, and you have your interval here, say you use 4 points, well, when you do the transformation back, you will get some kind of point in the middle, ends, and somewhere in between. Okay, for the first elements. And for the next one, you will have the same point here, which is the point of them, because then you can actually compare them. End point here, middle one, there, and so there. Between. The thing is that you want these points to overlap, so you can actually kind of transfer information between elements, in a sense. Okay, but in essence, you could pick whichever points you want. I mean, you could also pick the Gauss-Legendre points, but then you would have problems enforcing continuity between the elements. And you can also just pick uniform points, including the endpoints, but you wouldn't maximize accuracy doing this. So these are just some nice points to pick, so the GLL points. Some people sat down and just studied it and saw that, oh, these points give us the least error. Yeah. And next, I want to avoid writing these transformations. This, this, also this. So I'm going to introduce row tilde xi I similar fashion tilde equals xi f tilde xi f x xi b. So that's just, again, shorthand notation. Okay, applying this and using our newly acquired Legendre points, we're going to write the equation again. I think this is where we stopped yesterday. One to one. Xi, j, xi, li, x, d, xi plus n plus 1 ui e t dot this there. 1 mu psi psi lj I xi e x x squared psi. Well, not that much shorter, but it's 1 to 1 test function Lj psi t dx d psi. Okay. We still have some kind of, well, not nasty integrals, but we have integrals to solve. This is the weak formulation of the acoustic wave equation, where we've done a transform from x to a reference element xi, using Legendre polynomials as both test functions and basis functions. So it's basically this equation, only I've replaced all of the c's with the j's. Yeah? Yeah, Lagrange polynomials. Yes. Yeah, so Lagrange polynomials, those are basically just polynomials that are fitted to these points here. Those, because we want to reduce the error and also Runge's phenomena, and then some math guys have figured out we use the points. These are pre-computed. You have a question? Say again. Yes. That's from, you don't see it explicitly. It's just how we define these basis functions, these LIs, or LJs and LIs. So these polynomials come from, or polynomials, Legendre polynomials, come from these points. So you basically, you want to fit using these points. Okay, and then you have a basis set. And then you have a basis set of them. I could try to find code I wrote for it. Seconds. Okay, so it's similar to the Chebyshev polynomials. Look at this. Okay, so these are the so-called Chebyshev polynomials. They are defined from -1 to 1, and now they're just 4 of them. You see, 1 is just a constant here. Then I guess this third one, the yellow one, fourth, actually n plus 1. So these are basically what we have. These are the basis functions we have. Okay? So by doing a superposition of these, adding them in a good way, we can actually fit all polynomials inside this range. Say we wanted x squared. Well, that's basically this. And then you can move it using this polynomial And if you want a higher degree order polynomial, well, then you have to add one of the higher. Okay? So these are basically the same as the Legendre polynomials, only these are defined using different collocation points than these collocation points over here. Okay? No? Does it make sense? No. It's abstract. No, it's abstract. Okay, so you can have more of them, and you see you are able to fill the whole space. If you have an infinite amount of this, you will fill the screen. Okay? So these are polynomials. What is polynomial space? It's an abstract construct again. Okay, but you know 3D space. Okay, so what are basis functions of 3D space? Or what's a basis of 3D space? Not basis functions, but what's the basis of 3D points? So say you have, okay, let's first do 2D space. If I want to create something that can hit every point on my blackboard using 2 vectors, I can use this vector and this vector. Okay? Adding these two, I'm able to hit all the blackboard. Okay? I can also use these 2 vectors. I'm able to hit all of the blackboard. And they don't have to be perpendicular to each other, but it's more difficult. So it's easier if the vectors or the basis is perpendicular on each other. Okay? But if I have one vector going this way and the other one going this way in the same plane, I'm only able to hit or cover one line. So this is not a basis of 2D space or the blackboard space. Okay? In 3D, I need one extra direction. So maybe something to get us out here. Let's see. I have these two and an arrow pointing out. I'm able to hit every point in this room. Okay, so 3D space. Polynomial space is just polynomials instead. To say that you want to hit some kind of arbitrary polynomial, let's say 2x plus x squared, just as an example. Okay, then you can construct this polynomial using a superposition. A superposition is basically just a sum of basis polynomials. So here we are spanning functional space using polynomials. It's the same concept, it's just expressed in a different way. Okay? And when we're doing this transform, we have this, in space, we have kind of like a test cell, the test area. For instance, we are able to solve the wave equation inside this remote. Then we just need to figure out how can we scale this test element to fit how we've split up this room. So we can either just stretch it, or stretch it in this way, or squeeze it, and we can use functions to do this. And then it's easy to compare the room with this reference element. We could also just do all of this fitting for each of the elements, but then we need to figure out what's the collocation point to give us the lowest error for each and every element in this real space. Yeah? So if you instead just forget that idea and we have a reference element where everything is nice and neat, so with this remote, for instance, then we can do all the fancy maths there, and then we just need a linear transform. A linear transforms, that's just either scaling, squeezing, or rotating stuff. In 1D space, it's basically just squeezing or stretching stuff. It's a lot easier well, it should be easier to think abstract in that sense. So we have this one interval where we know all of these fancy stuffs that if we use these points, then we get the least error, okay? And then we can just, well, either squeeze or stretch it to fit our intervals. If you go to 2D space, it's more complicated again, because then you can both squeeze and stretch in the x direction and the y direction. So then you need more polynomials also. Okay? So we just have this kind of golden standard we want to hold our equations to. And yes, I know it's kind of advanced or abstract math, but please bear with me. Yeah. Then this. Okay, yeah, but it's good you ask. So I'm trying to explain. I thought I had this explanation earlier also, but it's good to repeat. So yeah. So was that a better motivation for why we were doing all of this fancy stuff? Yeah. Yes. That's why I wanted to repeat this stuff. So I thought maybe you weren't going to write down now because you wrote this yesterday. You were supposed to write this down yesterday because this is basically what I covered yesterday, just in a shorter form. So that's why I'm repeating it, because I know it's difficult to grasp. That's also why I take the time to just, well, explain it now, because personally, I find it very interesting or exciting also that you can do these kind of stuff in a controlled environment and then just hold it. Again, this is just 1D, so it's just an example. 2D, I'm going to skip that this time. But yeah, I think it's a good time to also have a 15-minute break. And then we'll put all of this to use in the next lecture, the next hour. Yeah. Yeah. If this was on an exam, I think it was 2 years ago. Then it's more just introduce the test function and just the thought processes behind it. Yeah, more theoretical. Mm-mm. I'm trying to motivate it while writing, but it doesn't always go through. I see. So that's why I'm also explaining it now. No, 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 no. Okay. Yeah. Good. I will take this to heart. Because I mean, this is the second time I'm actually lecturing course.